all right, third time's the charm. Let's try again. So welcome to the summer school. We're going to be talking about foundations and frontiers of probabilistic proofs. So this school is made possible with logistical and monetary support by MSRI in Berkeley and the Ethereum Foundation. We have 75 students scattered across different time zones. So be mindful of your time zone and the daily schedule. There's lots going on every day, 2 lectures and 2 recitations. But let's talk about it in detail. I would have prepared a few slides to overview the school itself, and then we'll switch to today's material. Okay. I'd like to first introduce the course staff. So we'll be running 2 courses with Tom and I as co-instructors. Tom is here, and maybe you want to say hi.
Hi, everyone. I'll see you in 2 hours too.
Great. Hi, Tom. And we have 4 wonderful teaching assistants, Gal, Inbal, Marcel, and Nick. Maybe some of you have already met Gal and Inbal, but maybe Gal, in this order on the slide, maybe each of you can say hi to the rest of the students.
Hi, everyone.
Hi. Marcel is currently stuck outside. Can't get into the room. But,
Okay.
Hello, everyone.
Yeah, and our teaching assistants are experienced researchers that have absolute experts in the material, so you should absolutely feel free to kind of bombard them with questions about the finest of points you can think about. And so they will be helping out with the recitations through the next 2 weeks. So we have 10 days. It's pretty... We're going to be, basically, it's like 2/3 of a semester compressed over 10 days, Monday through Friday, over the next 2 weeks. It's a pretty intense schedule. There's going to be sort of, really, it's like the same, a lot of material, but we try to kind of extract it and separate it into 2 courses. We call them course A and course B, okay, that sort of are semi-independent, but they will have like, some small connections. And every day, there's going to be a 1.5 hour lecture for each course and 1 recitation for each course. Okay. The lectures are on Zoom, and they will be available as recordings shortly thereafter. Okay, basically as soon as we can process the file and put it on YouTube, and we'll let you guys know about the playlist and Slack. The recitations are also on Zoom, but they're not recorded, and so this is meant to be like an interactive school. We try to pay attention to your time zones. So in particular, you have been assigned to a specific recitation group. There are 4 of them, G, I, M, and N. You are required to attend the recitation in that group square bracket group. And not only that, we also have office hours every day, 2 hours. We'll collectively be covering it. Sometimes it will be some subset of the staff, some other time. All right. So today's office hour will be like mostly informal. We'll mostly try to hang out there and just say hi, and we can. If you have questions, of course, that are technical, please come. But otherwise, try to socialize.
Yeah, there's an echo again now.
But how is that possible?
I don't know if it's an echo or whether it's a software problem, though.
But now. There's no echo anymore?
Seems okay.
This like really threw me off. Like I have an extremely battle tested setup and not quite sure what's going on. I'll try it offline. Sorry about that. Right, so today's office hour is mostly for socializing, but please bring technical questions as well, that's fine. In addition to having been assigned recitation groups, you have been assigned working groups. That is a small group of 3 to 4 people that we kind of sort of put down that we chose ourselves, like paying attention to your time zones, and you're required to collaborate within this group as far as worksheets during recitations are concerned. So during recitations, that we have prepared worksheets that we'll be going through and putting you into breakout rooms to chit chat about those problems, and we will be kind of breaking you up according to these working groups. So please make sure you look up your working group and see who you've been assigned with. And certainly, do reach out and say hi to your working group peers. And we encourage you to sort of communicate in the way that is convenient for you with them. Again, this whole setup is a bit of a first time, not just the material, but the fact that it's online with so many students across time zones. If you have any feedback, please let us know. I think we have a structure that will work well for the next 2 weeks, but honestly, we don't know, okay? All right. So just a couple of words about software. We have this pretty nifty software that has worked well for online schools of MSRI. It's called Sococo. It's like a virtual space, literally, like there's a snapshot of it. There's a screenshot of it. You can reach the lecture room by just appearing in that room and just clicking on the Zoom link if you don't want to go to the daily schedule. Us staff, whenever we're online, will appear as like little avatars in our offices, and you can just like double click on the office and show up there and say hi. There's also free offices if you want to hang around and you're maybe working on stuff, but you just want to show that you're online and other people can just drop in the office. We also have recitation rooms where you can find the Zoom links for recitations, this hangout area. And we have also created working group rooms that you can use if you find Sococo useful to just put your avatar in the same room as other people in your working groups, and you can use it. It has worked well for past summer schools last summer. So I think it's worth giving it a shot. For Slack, it's basically for all course communication. These are the main channels. Please pay attention to the general channel. There is they're pinned announcements with the daily schedule, the roster, and the materials. This includes the worksheets and the lecture slides, which I forgot to put online before my lecture. I'll put them after. There's a channel that has had a little bit of traffic over the last few weeks, primarily for background questions and references. There's a lecture channel where you can ask discussion and questions about lecture. And then we have 4 recitation channels for the respective 4 recitations. And more an informal channel. Private questions, again, please DM us. And for working groups, you're encouraged to create your own Slack channels. They're private. We cannot see what's going on there. It's sort of your own communication between you and your peers. Okay. Any questions about the logistics? We're kind of done with the logistics of all right. So what about the material? So this is the plan. We have these 2 parallel courses, 2 lectures per day. There is going to be some introductory lectures today for, oopsie, that's not what I meant, for interactive proofs and PCPs. And then we have tried to kind of refactor the material in some sort of coherent units. There's a unit on interactive proofs, constructions of interactive proofs. There's a unit on property testing, which is warming up to constructions of PCPs. Indeed, that's what follows. And then we'll talk about interactive oracle proofs. You may be familiar with some of these terms or not, doesn't matter. We'll introduce all of these things, and we're supposed to kind of take you from the declared background, okay? So that, up to day 5, that would be the first week, and then that would be, the second week. Any questions about the course plan? Yeah, so that's what we'll be doing. So we have provided some background references well in advance, but just to remind you, we will be assuming understanding of finite fields, basics of linear codes, being able to understand properties of univariate polynomials, multivariate polynomials over finite fields, basics of complexity theory. So that means models of computation like machines, circuits, NP reductions, the Cook-Levin theorem, basic complexity classes. So for example, like a picture like this one of complexity classes should look reasonably familiar to you. And if not, we have put in the background channel references that will help you with that, okay? And our goal is for the next 2 weeks, to take you to the point where you can understand different models of probabilistic proofs. Specifically for this course, it means interactive proofs, probabilistically checkable proofs, interactive oracle proofs, okay? So you should be able to understand what each of these models are, understand kind of their power, how can you sort of probabilistically check hard problems beyond BPP, how and why do these models enable exponential savings in communication or verification time, how is it possible to achieve properties like zero knowledge? So kind of all of these things sort of if you stick through the material day by day, in 10 days, you should be able to do at, quite precise and technical level, okay? And then, this is kind of to take you to the research frontiers. You should be able on your own to be able to kind of design and analyze new probabilistic proofs. Okay, that's kind of the intended goal, is to bring you to the research frontier where you can work there. Okay. Again, please write in chat if you have questions. I keep looking at it with my eyes, and if you have questions, just interrupt me also. Great. So just a few words about why should anybody care? I mean, there's lots of technical material out there, and it takes time and energy to learn it. So why this particular technical material? There are a number of, let's say, kind of independent reasons to care. One is, let's say, primarily, let's say, intrinsic or philosophical in nature. This cluster of material about probabilistic proofs, it is a beautiful re-envisioning of what does it mean to prove to somebody else that some theorem is true, okay, or some statement the claim is true is indeed so. That is distinct from and an evolution from the notion of a mathematical proof that has been primarily unchanged for many years, basically until the 80s when these models were formulated. So they're just kind of intrinsically interesting as sort of formalizations of the notion of proof. But then, in a more kind of utilitarian perspective, they're just very powerful set of tools to solve problems that are a priori not necessarily about probabilistic proofs. So these have applications to privacy and scalability in cryptography. They have connections to algorithmic questions such as hardness of approximation. And they also help us understand what you could say are physical phenomena, such as the power of entanglement, okay? With this, perhaps one of the best illustrations of this is the last year's sort of achievement of proving that the MIP star, a certain class of entangled probabilistic proofs, can express every recursively enumerable language, okay? Which is sort of a landmark result at the intersection of physics, mathematics, and computer science. And it was, all made through the perspective of probabilistic proofs. So there's powerful theoretical tools, okay, even if you don't care about philosophy. And if you're more practically inclined, sort of especially through this connection to cryptography, because probabilistic proofs let you construct nifty cryptographic objects, specifically what I will informally discuss here as super efficient cryptographic proofs. The way you construct them is that at their core, at their heart, there is like some engine, and is made of probabilistic proofs. Okay, somehow we wouldn't have the faintest idea how to construct these super efficient cryptographic proofs if we didn't have an understanding of how to probabilistically check computations. Okay, and because we have efficient probabilistic proofs, therefore we are able to construct efficient cryptographic proofs, and these have applications in distributed systems. For example, privacy-preserving digital currencies, scalability tools. You may have heard architectures such as rollups in blockchains. Well, they're based on cryptographic proofs. And many other things, including just fun things like fun peer-to-peer games. Here's a screenshot of a game called the Dark Forest that runs decentralized thanks to zero-knowledge proofs that themselves are based on cryptographic proofs, which themselves are based on linear PCPs. Okay, so ultimately, at the bottom of this all, the fact that we have efficient zero-knowledge proofs is because we understand how to construct efficient probabilistic proofs. Okay, and all up the way up the top, you have very interesting sort of innovative architectures about games, of all things. Okay, and so, and over the past 10 years, there's really been sort of a truly exciting development, especially on the applied side, thanks to many innovations on the theoretical side that has given us much more efficient probabilistic proofs than we had, say, 20 years ago. Okay. Any questions about the motivations, or so this is just like really brief introduction, and just as a warning, most of the course will be truly technical and not focused on applications. The reason for that is that there is a wealth of descriptions of applications and blog posts and videos online about what cryptographic proofs are useful for, but it's much less of a sort of a set of didactical materials for actually learning about the technical aspects of probabilistic proofs. So this will be like a highly technical course focused on the mathematical aspects. But here I'm just pointing out that, beyond these, there's like a bunch of applications that, with this expertise, you can appreciate more or work in, right? I think that's all I had in terms of introductory slides. That's, I think I'm just about on time, despite the mic mishaps. Before I switch to the, let's say, technical part of today's lecture, any questions?